Yes. So I got the result of maximum demand from the load schedule. So after getting the maximum demand, I am calculating maximum demand into 1.1, take some margin of 10%. This value of X kVA, I am telling this is the transformer capacity I required for my system. This is absolutely fine. Or DG set capacity. This we will call as a steady state approach. Steady state approach. So what is the next one? But in the auxiliary transformer sizing or in the DG set sizing, instead of addition to the steady state, we have to do the transient analysis also. Transient analysis. What is this transient analysis? Let me clear you that. Transient analysis is, team, suppose this is my auxiliary transformer. This auxiliary transformer is connected to 1, 2, 3, 4. 4 loads. Load 1, load 2, load 3, load 4. This load is lights. This load is a motor. This load is some air conditioners, the ACs. And these loads are for the fire pumps, those. These loads are going to that. So out of this, this is the biggest motor. Okay. Now in the transient analysis, what we will do is, if all the loads are in service, means this load is on, means entire, all the loads are on. All ACs are on. And the fire motor is also on. If all these on, then if I am turning on this motor, the largest motor in the system or the largest load in the system, if I am turning on this motor or the largest load, at the time of remaining all loads are on, when I am turning this motor on, you know that when the motor is turning on, this motor will run at the starting current of motor is very, very high. And the power factor is very, very less. Resultant to the kVA rating of the motor is obviously higher, very higher compared to the normal rating of the motor. And this extra kVA will impact on the transformer for some period of time, that is a transient. So I have to check whether my transformer can able to withstand for that extra kVA which required for the motor for some period of time. If my transformer is well suits to view that, absolutely my transformer design is fine. Understood, team? Suppose, let's see here. In a normal case, the total loads of the light is 2 kilowatt. And the ACs, 5 ACs, nearly 10 kilowatt. And the 5 pumps, each of 6 kilowatt, and 4 motors are there, 24 kilowatt. And this is the motor, which is 7 kilowatt. So what is the connected total load? I'm talking about the demands, not total load, demands. 7, 8, 9, 19, 19 plus 24. Right? So it's nearly 43 kVA is the required capacity for your transformer. So 43, I am taking a 10% margin, which is 50, suppose 50 kVA. So this is my transformer rating, 50 kVA. I selected the transformer rating is 50 kVA based on this. This is my steady state approach. Now, when all these are run, like 24 plus 10 plus 2, which is 36 kilowatt is already in service. The 36 kilowatt is the load at present on this transformer. Now I turn on this motor, which is 7 kilowatt. And suppose the voltage level is, let's take 415 volts supply, 7 kilowatt motor. Then what is the current? Let's do the calculation. Where's the motor? 7 divided by 1.732 divided by 0.415 gives me 9 amps, 9.7 amps, whatever it may be. So 9.7 amps is a rated current, or 10 amps. Let's take 10 amps is a rated current. But in my manufacturer catalog, it was said that when you are turning on the motor, the starting current of the motor is 6 times. And the power factor is 0.3 only. Then 60 amps at 0.3 power factor, and the voltage level is 415 volts, then what is the power required? 1.732 into 0.415 into 60 amps into 0.3 gives you 13 kilowatt. My motor at present, it's not a 7 kilowatt motor, it's required a 13 kilowatt here. So now the demand of this load during the starting is not 7, it's nearly 13 kilowatt. 6 times, right? So it won't be nearly 13K, it would be more than this. It's come to nearly 43 kilowatts something. Suppose, let's see the calculation, because here the starting current, the power factor I am giving here is 0.3, which is sine. If I'm converting to the cos, everything, that it would change. So it's resulting to 43 kV. So the 43 kV is the load I required, suppose, for time being. Let's see. But my present load is 7 kilowatt, but it is asking 43 kilowatt from the transformer. So then what is the total load? 36 plus 43, 979. So 79 kilowatt is the requirement from the 50 kVA transformer. So when I am designing the transformer as per the IEEE IEC 354, IEC 354, yeah, IEC 354, table 1, it was mentioned that the transformers are capable to withstand 150% of the loading during the transient condition. It seems that this transformer can be loaded up to 50 into 0.15, which is 75 kVA up to in the thermal loading, in the transient condition. But my requirement is 679 kilowatt. So this won't be the sufficient. Then what I have to do, I have to go for the next design. If you want, you can do like this also, like 79 divided by 1.5. So what is the requirement? 79 divided by 1.5, which is 52.6. So in the market, if you are having 60 kVA or 55 kVA, you are purchasing that transformer. Even though it is satisfying the steady state, it is failing to satisfy the transient approach. So I have to select the next size of the transformer, which is 55 kVA or 60 kVA. Understood, team? Clear? Yeah. So let me share you that calculation one. Are you able to see this one? Calculation sheet. So here you can see that this is a steady state calculation, the maximum demand 9320. Just I'm multiplying with this 1.1. This is the result. So I selected 12.5 MVA transformer. Now I'm checking for transient. What is the base load? By removing the motor rating, I found the base load, and I'm calculating the motor load current, and I'm calculating the full load current of the motor for the motor. And the starting current is obviously 6 times of the full load current. And it was mentioned that in IEEE 325, it was mentioned that take 20% tolerance on this. So this is the tolerance. And what is the starting kVA of the motor now? It is 9947. So this starting kVA plus the base load gives me this. This is my base load. Now but I selected is 12.5 MVA, but I required is 17.86. But in that IEEE 354, it was mentioned that this 12.5 MVA can withstand up to 18.75. So which is 17.88 is less than this. So the selected 12.5 MVA transformer design is quite good for my approach. So after this, I am calculating the voltage drop during the largest motor starting. This is the formulas, big formulas. This is a during transient. I have to calculate, and I have to calculate the steady state voltage drop also, like I into R cos phi plus X sin phi. That also I am calculating. And I am finding that what are the voltage limits, tabulating here, that the thermal loading on the transformer is this, the required is this. Thermal loading on the transformer during motor starting is 143% only. If I'm dividing it with 17,886, but my required is 150%. So it is also in safe. And I'm calculating what is the voltage available at motor terminals during the motor starting. This is the value I got. It can be acceptable up to plus or minus 15%. During the motor starting at buses is 10%, plus or minus 10%. I got 91%, so it is also fine. And voltage available at motor terminals during not starting, it is wrongly written. This is at steady state. What is the voltage available at motor terminals during running? It is recommended at plus or minus 5%. I got 99.66%. So all conditions are satisfied. So I can say that 12.5 MVA transformer is a safe for me. So this voltage drops depends upon the impedance of the transformer. And also in the transformer, we have to take the next one is the tap rating and the vector group. So the vector group, impedance, and the tap ratings, we will continue in our next class. It's again a big topic, the vector group impedance. So for time being, just concentrate up to the transformer sizing. And what is the reasons to select the DYN11? Why can't we DYN5 or YY? We will discuss in the next classes. And the impedance value is also same thing, which you have to select based on some scenarios like short circuit calculation or depending on the losses, other things. So that also we will cover in our next class. For time being, this is the subject. This is the topic for the auxiliary transformer as well as the DC set size.